Hello, my name's Keith Cooper. I'm a benthic ecologist and data scientist from CFAS in the United Kingdom, and I'm going to be talking to you about OneBenthic, a big data approach for sustainable use of the seabed. So, as you may be aware, big data offers huge potential for improving environmental sustainability, and there's a growing literature around this subject. OneBenthic is a big data initiative which turns publicly available data into new information, leading to more sustainable use of the seabed. So as you'll be aware, there are lots of activities going on offshore with industry and government, and these activities are generating huge quantities of benthic data. So these are grab and core samples that are processed for macrofauna and sediment particle size. These data end up in multiple repositories and databases, and if you want to do anything with these data, we need to bring them together, and that's the purpose of OneBenthic. So data are brought together, disparate surveys, in one Postgres platform within the cloud. Data is standardized according to the World Register of Marine Species, and the data set is used to generate new science and data products. And we've got a series of web apps which are available from the CFAS Open Science site. So all these outputs lead to better decisions and improved sustainability. So this is the dashboard, which gives you a view of what's in the database. A little fly through here as well, showing sample locations. And just draw your attention to the number of samples here. So we're nearly up to 43,000 samples from over 800 surveys, and these data are worth over £21 million just in terms of sample processing costs. So how are these data being used? I want to give you a couple of examples now. So the first is the point sample data have been used to create a 100% coverage layer for macrofaunal assemblages. And this is really useful for characterization, marine spatial planning, and it can reduce our reliance on physical habitat classification approaches, where strata are often used as a proxy for the biology. In the second example, we developed a new monitoring approach for activities which change the composition of sediments. So for example, aggregate dredging, which is the removal of sand and gravel from the seabed, can lead to changes in sediment composition as a result of exposing material which is different in nature to that was at the surface originally, or through the selective removal of certain sediment fractions. So for example, if they take the gravel and reject the sand. So if these changes don't resolve themselves naturally, which they often do, then this can have implications for recovery. And as a result, there is a license condition which says that seabeds sediments need to be in a similar state to those which were present before dredging. The difficulty is in deciding what similar means. And in order to get that perspective, we're using the data set, the big data, to do that. So we have samples assigned to different assemblage types, and we understand the range of sediment composition that's found in association with each of those groups. And it's that insight which we're using to make judgments as to the acceptability of sediment change within extraction areas. Here's how it works. So this is one of the aggregate producing regions in the Thames off the east coast of the UK. So you can see these polygons are extraction areas and secondary impact zones. The red dots are sample locations. So there's a baseline survey, and then subsequently these sites are monitored, and all that survey work is covered by a protocols document. So at the baseline, we're looking to identify the nature of the faunal communities that are present within the regional array. And to do that, we're using a faunal cluster ID tool, which takes new macrofaunal data and matches it to the existing cluster groups. Having established the baseline, we then move into monitoring. So what we do is we monitor each of these aggregate producing regions once every 4 to 5 years. We look at whether there's any evidence of statistically significant changes in sediment composition, and we do that at a variety of different spatial scales. This tool uses a combination of ordination, ANASIM, and SIMPA analyses, and if there's no evidence change, polygons will go green. If there is evidence of change, they'll either go yellow or red, depending on the scale of that change. In this other tool, we're looking at whether changes at individual points, changes in sediment composition, are likely to be a problem for recovery, and that's done on the basis of a Mahalanobis distance test. So this new approach to monitoring offers multiple advantages. So it gives us better environmental protection as a result of having a clear scientific rationale, consistent better quality data, having a regional approach to monitoring. having the ability to differentiate between statistical and ecological significance, moving away from reliance on expert judgment and using data to make decisions, having a simpler assessment and reporting process, and allowing outputs to be used for adaptive management. It's also helped reduce the cost of monitoring by 50%. So if you want to find out more, there's a few links here. You can access the apps I've shown from the CFAS Open Science site. I should also just thank the funders for supporting the initiative, and thank you for listening.